US Physics Olympiad, year 2020, USAPHO, final round. Problem B1. String cheese. Question A. When a faucet is turned on, a stream of water flows down with the initial speed v0 at the spout. For this problem we define y to be the vertical coordinate with its positive direction pointing up. Assuming the water speed is only affected by gravity as the water falls, find the speed of water v as a function of y at the height y. Define the zero of y such that the equation for v square has only one term, and find y, the height of the spout. Question B. Assume that the stream of water falls from the faucet is cylindrically symmetric about a vertical axis through the center of the stream. Also assume that the volume of water per unit time exiting the spout is constant, and that the shape of the stream of water is constant over time. In this case, the radius r of the stream of water is a function of vertical position y. Let the radius at the faucet be r0. Using your result from part A, find ry. If ry is not constant, it implies that the water has some radial velocity during its fall. In contradiction to our assumptions in part A that the motion is purely vertical, you may assume throughout the problem that only such radial velocity is negligibly small. Question C. The water-air interface has some surface tension sigma. The effect of surface tension is to change the pressure in the stream according to the Young-Laplace equation. Delta P equals sigma multiplied by 1 over small r plus 1 over big R, where delta P is the difference in pressure between the stream and the atmosphere, and the big R is the radius of curvature of the vertical profile of the stream visualized below. R less than 0 for the stream of water. The radius of a curvature would be positive only if the stream profile curved inwards. For this part of the problem, we assume that absolute value big R much greater than absolute value small r, so that the curvature of the vertical profile of the stream can be ignored. Also assume that water is incompressible. Accounting for the pressure in the stream, find the new equation relating for ry in terms of sigma, r0, v0 and ρ, the density of water. You do not need to solve the equation for small r. Question D. After falling for some distance, the water stream usually breaks into smaller droplets. This occurs because small random perturbations to the shape of the stream grow over time, eventually breaking the stream into a part. For the rest of this problem, we ignore the change in the radius of the stream due to changing speed of the water, as considered earlier. Instead, we examine small random variations in the radius of the stream. Random variations can be broken down into a sum of sinusoidal variations in a stream radius, each with a different wave number k. We can analyze these different sinusoidal variations independently. Consider a stream of water whose radius obeys ry equal r0 plus a cosine ky, where a much less than r0 is the perturbation amplitude. To analyze such a stream, it is sufficient to consider only the thickest and the thinnest parts of the stream. According for both sources of curvature, find the condition for R0 and K such that the size of perturbations increases with the time.